Hi students, once again welcome back to this tutorial, and in this video we can discuss some of the important previous year university questions that are based on our module 1 of our subject logic system design. So we can start with this particular question, that is, a number is given, a positive number 12 is given to you. Okay, and you are asked to get the 2's complement representation for this given number positive 12 in decimal system. Okay, the given number is positive 12, and you are asked to get the 2's complement representation corresponding to this positive 12. How to get? So we know that for all the positive numbers, we have the same representation in signed magnitude form, in 1's complement form, as well as in 2's complement form. Okay, note this point. For a positive decimal number, the signed magnitude form, the 1's complement form, and the 2's complement form all are the same. But in case of negative numbers, they are different. So here the question is a positive number. In that question, the number is a positive number, which is positive 12. Okay, so it is clear that 1's complement representation, 2's complement representation, and signed magnitude representation all are the same. Then what is that representation actually? How to get the representation? So we need to concentrate here in the signed magnitude form, and how to get signed magnitude representation for this positive 12. This is positive, means sign is positive. For the sign positive, mark 0. If it is negative, the sign magnitude representation, the sign is represented as 1. If it is a positive number, the sign is always 0 in sign magnitude form. Okay, now we need to get the magnitude. How to get the magnitude of this decimal 12? We have a rule to get the the binary, or the binary for this decimal number 12. What is that? So how to get the magnitude of positive 12 in binary? So for that we have a particular rule, that is divide this 12 using our base of binary, that is 2. So while dividing this, we get a quotient, that is 6, remainder 0. So write the quotient just down here and write the remainder over here. Then again, the 6 is actually greater than our divisor 2. So again divide the 6 using our same base value 2. Now we get the new quotient as 3 with the remainder again 0. Okay, now we can divide this 3 again using our same base value 2, because this new quotient 3 is again greater than our divisor 2. Okay, so continue this. Now we get a quotient, that is 1, and a remainder 1. Right? Now our new quotient is 1, which is less than our divisor 2. Now we can stop here and arrange all these values, all these bits in this particular order. Okay, so now we get the representation for positive 12 in sign magnitude form, which is positive means positive sign. So put a 0 for indicating the sign. Then arrange this binary bits. This will form the magnitude, that is 1100. So this is the signed magnitude representation for this positive 12. Right? So we have a point, that is for a positive number, signed magnitude representation, 1's complement representation, 2's complement representation all are the same. Right? So this will be the 2's complement form of positive 12. Okay, this is. Now consider the case. Suppose the question is like this. We need to get the 2's complement representation corresponding to a decimal number minus 12. Decimal number minus 12. Okay, then in that case, we have already said for a negative number, 1's complement representation, 2's complement representation, and the sign magnitude representation all are different. So how to proceed such a question? For in this case, now if the given number is a negative number, how to proceed? So in this case, first identify what is positive 12. positive 12 in sign magnitude form. Okay, positive 12 in sign magnitude form is 0. Sign is 0. Then magnitude of 12. We have already derived that binary pattern for magnitude 12, that is 1, 1, 0, 0. Okay, this is actually positive 12. Okay, after getting the signed magnitude form of this positive 12, we can stop here. Next step, get the ones complement form of this pattern, this positive 12. Okay, actually our question is getting the 2's complement form for minus 12. And the first step is write the signed magnitude form of positive 12. Note this, write the sign magnitude form for positive 12. Question is 2's complement form for negative 12. So the first step is write the sign magnitude form of positive 12. So the sign is 0 and this is the binary pattern corresponding to magnitude 12, that is 1, 1, 0, 0. Second step, get the ones complement form of it. That is, simply convert all 0 with 1 and all 1 with 0. That is the ones complement representation. So here it form 1, 0, 0, 1, 1. Right? So this is the ones complement form. Then what is next step for getting the 2's complement form? After getting the ones complement form, add a single 1 with this ones complement form. So by adding a single 1 with this, we get 1 plus 1. Value is 2. 2 in binary is 1, 0. That means put the 0 here and pass this 1 as a carry to next level. Then 1 plus 1. 1 plus 1 again, the value is 2. 2 in binary is 1, 0. So put that 0 over here, pass that 1. M must be 1 as a carry to next level. Now 1 plus 0, 1, 0, 1. So this will form the 2's complement representation corresponding to our minus 12. Okay. Next question is get the 2's complement representation for minus 15. Okay, 2's complement representation for minus 15. Okay, so start with positive 15. Write the sign magnitude form for this positive 15 first. Sign is positive, so it is sign means positive. Then that sign is represented using a bit 0 in sign magnitude form. And for 15, the binary pattern, we know that the binary pattern for this 15 is 1, 1, 1, 1. Okay, so this is the signed magnitude representation corresponding to positive 15. In order to get the 2's complement form of this minus 15, after writing the sign magnitude form of positive 15, next step, take the 1's complement form of it. That is, this 0 become 1 and all the 1's become 0. Simply convert 0 with 1 and 1 with 0. That is the procedure for getting 1's complement form of a given binary pattern. So after getting this, in order to get the 2's complement form, simply add a 1 with the 1's complement form. Okay. So we get 0 plus 1 is 1. Again 0, 0, 1. So this is actually the 2's complement representation corresponding to minus 15. And what about this positive 15? Suppose the question is like this. In order to get the 2's complement form of positive 15, the number is positive. So this procedure is simple. That is the sign magnitude form, 1's complement form, 2's complement form. For a positive number, all are the same. So simply write the sign magnitude form of this positive 15. That will form the 2's complement representation also. So for positive, the sign is 0. Okay. Then for 15, the magnitude is 1, 1, 1. This is positive 15 and negative 15. So after getting this positive 15, take the 1's complement, then add 1. So this form minus 15 and this form positive 15 in 2's complement representation. So this is the procedure. Okay. Okay, next question is a subtraction operation in 1's complement form. We need to perform the subtraction with the help of 1's complement operation or 1's complement principle. Okay, so this is actually our this is actually, we can consider this as a minus b. Okay, so this a minus b can be rewrite as a plus minus b. A minus b can be rewrite as a plus minus b. So in that case, take this a or place this a as it is here and take the 1's complement form of b. 1's complement form of the given b form minus b. Then simply add these two values. This is the procedure. If we want to perform a subtraction operation using 1's complement principle, what we want to do, if a minus b, that is the operation we need to do, in that case what we want to perform, the first step is a minus b can be rewrite as a plus minus b. That minus b, how to get that minus b? Minus b means negative of b. Negative of b means 1's complement of positive b. That positive b is given here. Take the 1's complement of it and simply add a and that 1's complement form of positive b. Okay, so this is the question. Okay, this is a and this is b. So this is b. Okay, take the 1's complement of it. 1's complement 0, 1, 1, 0, 0. Right? Then perform addition. A plus minus b. This is minus b. Okay, this is minus b. Now a plus minus b. A is what? 1, 1, 0, 1, 0. Add with this one. 0, 1, 1, 0, 0. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 means value 2. 2 in binary is 1, 0. So put that 0 here. Pass that 1 as a carry to next level. Here it is 1 plus 1 plus 0. 1 plus 1 is again value 2 in decimal. That value 2 in binary is 1, 0. Put that 0 is 0 here and pass that 1 as a carry to next level. Here we have no other bit for addition. So simply write this one here. Okay. In 1's complement addition, if such an end carry occurs, what we want to do next? Simply add that end carry with the remaining bit. Then we will get the result. Note that point. In case of 1's complement subtraction rule, after performing this a plus minus b operation, if such an end carry occurs, simply add that end carry with the remaining bit. Then we will get the exact result. This is the rule. Next is about a subtraction in octal system. Subtract this number which is in base 8. This is in base 8. Subtract this this 3 2 in base 8. Subtract from this 7 to 1. But these numbers are not in decimal, they are in octal system. Okay, so this is again a university question. How to perform this octal subtraction directly? So the rule is the same, that is possible in decimal system. 7 to 1 minus 3 2. Okay, so 1 minus 2, this subtraction 1 is actually less than 2. So this 1 minus 2 is not directly possible. So in that case, we need to take a borrow from its next neighbor, that is from here. So while taking a neighbor from this position, this 2 is reduced. 2 get reduced by 1 and it form 1 now. 2 minus 1 is 1. And that reduced 1 is passed to this level. But that passed 1, here it form 8. Because the base is 8 here. Okay. So here it form 8. Then 8 plus 1 is 9. 9 plus 2 is 7. Okay. So the answer is that particular subtracted value is 7 here. Now 1 minus 3. 1 is less than 3. So 1 minus 3 is not directly possible. We need to take again a borrow from its next neighbor, that is from this position. Right? So by passing a value to this position to its neighbor, here it reduced by 1. 7 minus 1 reduced by 1 means 7 minus 1. Now here it is value 6, and that reduced value is passed to this level. So that value after reaching here, it become the base value 8. So that 8 plus 1, this is 9. 9 minus 3 is 6. Right? Here we have a 6 remaining here, and here we have no other bit. That means here it is 0. 6 minus 0, that is 0. So this is the result of this subtraction. Directly perform this subtraction, and this is the result. Difference value in octal system. So question is given like this. Square root of 224 in base R is equal to 13 in base R. Okay, 13 in base R. We need to get the value of correct value of this base R. Okay, how to get? This is actually based on our base conversion rule. Okay, so how to get the decimal equivalent for a given number which is in any of the base system, how to get, or what is that general rule? If a number is given in a particular base R, how to get its decimal equivalent? The procedure is like this: R raised to 0 into 4, first number, plus R raised to 1 into 2, second number, plus R square into 2, means add all the value present in a position with its weightage. Find the value and the position weightage, then all these terms together, and this is actually square root, so apply half, or power is 1 by 2, which is equal to 3 into r to the power 0 plus 1 into r to the power 1. Okay, how to avoid this half? For getting or for reducing this power term half, simply take square root of both LHS and RHS. Then this become 2r square plus 2r plus 4 into r raised to 0, that is 4. R raised to 0 means 1. Any term raised to 0 means 1. So 4 into 1, that is 4. This is 3 into r raised to 0. Again 3 plus 1 into r raised to 1, that is r. And take square here. In order to avoid this square root over here, simply take the square of both LHS and RHS. Now it become like this. A plus b whole square is 3 square plus 6r plus r square. Okay, and here it is 2r square plus 2r plus 4. Right? Now rearrange 2r square minus r square. Here we have r square and this is 2r square. Now it is r square. 2r and here it is 6r. 6r, now it become minus 4r. Here it is 4. Here it is 9. 3 square is 9. Now it become minus 5 here. Okay. So solve this equation and we get two values. One is positive 5. One is positive. For r, we get one value positive 5 and other is minus 1. Okay, here we have two values. And for a base value, a negative value means it is invalid case. So simply discard this minus value for the base r. So this will form our base value or the exact value for our base 6. Okay, thank you.